So in this video we're going to introduce Aspen and how to use it at Aberdeen. We're going to go from logging in on the VDI to configuring what components that you want to actually study. We're also going to configure the fluid package. We're going to use Peng Robinson in these tests here, and then we're going to show you how to use that. For example, we're going to calculate phase diagrams and mollier charts, and then we're going to look at a three-phase separator before we add on a couple of other components like a compressor and a cooler. We're also going to look at some advanced applications like using an adjust loop, and we're also going to look at what happens when things go wrong. So I'm going to just use this use Unisim as I would normally. Errors are going to arise, and I'm going to fix them and show you how I fix them. This isn't meant to be an extensive overview of Unisim. It's just meant to show you how you can get something done on it and look up some of the properties that we might be interested in this course. First thing you need to do is go to vdi.aberdeen.ac.uk and from there log in. Then you need to choose if you have a choice, you should choose the STEM, Science, Technology. Is it Engineering and Mathematics? This will boot a computer for you that has all of the engineering mathematics applications installed, and that includes Unisim and it also includes Aspen, and those are the two process simulation packages that we have available at the university. I am going to show you where both of them are, but we're only going to look at Unisim. I will try and upload some videos on how to use Aspen as well, given by another lecturer in the school. But we've standardized around Unisim for most of our applications. It should be noted that actually historically both Aspen and Unisim were actually the same code, but when it was sold to Aspen, it was actually forcibly sold also to another person, which was Honeywell, and they basically it was sold to two developers to prevent one person getting control of perhaps the most important piece of software available for process engineering. Right, so if you click on the folder here for physical sciences and then choose engineering, what you'll see down here is Unisim design, and that's the way I boot Unisim. And the other option that you'll see is Aspen up here, and Aspen has many different tools. Aspen HYSYS is probably the closest to Unisim. Well, maybe I'm thinking about Pro 2. Pro 2 is the old name for it. Anyway, Aspen HYSYS is here. However, what I would say is because we have Aspen Plus, I would recommend that you familiarize yourself with Aspen Plus, because Aspen Plus can do everything that Aspen HYSYS can do and a whole lot more. So Aspen's more or less the kind of current market leader, and there's plenty of materials to learn how to use it. But I'm going to go talk about Unisim because that's the one that has slightly less materials about it. So all you do is start up Unisim. What I will say though is because they're basically the same fundamental code base, or they have roots, shared roots, how you use them is very similar. I quite like using Unisim because it's a bit simpler as well, mainly because it can't do so much. Okay, so once Unisim opens, the first thing you're going to do is start a new design. And so you hit this blank paper in the top corner, and the first thing that it's going to load up is the component selection. So the first thing you need to tell Aspen or Unisim is what components you want it to consider inside your system. So this includes all of the chemicals you might be considering, any of the hydrocarbons, water, and so on. Now you don't say things like water, you say things like H2O, because when you add water, the component, you actually add steam, liquid water, ice, and so on. It's been a bit slow today. One of the things I will say is we have a limited number of licenses for Unisim and a limited number of licenses for Aspen. So sometimes you might get a license error. That's usually because too many people are trying to use it at the same time. I haven't seen that in a very long time, but when there's a design project going on, it can get a little bit contentious. So just try again later if you don't get it. Okay, so here we are on our basis manager. The first thing we need to do is choose what components are in there. You can have several component lists if you want to kind of organize them in some way, say so that you can, for example, import and export them. But we'll just edit the master component list, which is already there for us. If I hit view, what you'll notice is that in the selected components column, there's nothing here, right? So we have nothing. In the traditional library components, I've not actually picked anything. What you would put here is all of the pure compounds that you can identify. So for example, if we were going to work on CO2, say we had a gas coming out of the ground and it had methane, ethane, propane, and ibutane and so on, Then we'd also want perhaps some water as well, and rather than, I know water's right there, we can actually search for it just by typing up here, and you see that lets me add water. What else would we need? Well, that's a good selection of compounds, but if we're going to do kind of a gas system. But if you were going to look at an oil system, you would actually want to add some hypothetical components. So hypothetical components are available here, and right now we don't have any hypothetical components, so we're going to create one. Once you get used to this, you can hit these quick create programs if you want to, but we're going to go into the hypo manager here. So we're going to add a hypothetical group, and you can see here what it's going to be is it's going to be some hydrocarbons, and you can pick other kinds and have different kind of correlations you can use, but we're going to stick with hydrocarbons because that's what we look at the most in this course. And you can add a hypo, and you can name that hypothetical component, and you can put in details from an assay. So when people do an assay test on a well, they will tell you what properties should go in here. So for example, this is the normal boiling point, this is the molecular weight, liquid density, critical temperature, critical pressure, critical volume, and the eccentricity. And if you remember our physical properties lectures, you'll notice that those are key properties for correlating the behavior of fluids. There is also some other things you can do. For example, I'll just remove this hypothetical. I can actually, if I remember right, if I come down here, I can do a crude hypo. So a crude hypo is a very specific type of hypothetical, and what you actually do is you, instead of just boiling the whole thing off, you will actually say, look, starting from C5s, right, starting from C3s, C4s, C5s, I started to boil the compound, and every 50 degrees, I would, get I got 4 different cuts ending at like 300 degrees or something like this. And sorry, the first, starting from say 100 degrees C, every 50 degrees C, I had 4 of these cuts that gave me up to 300. So basically what would happen is somebody would boil some crude, so they would assay the crude, and then they would look for what would start to boil off at 100 degrees Celsius, say, and then every 50 degrees C they would collect what had boiled off, and then they would measure it. So then once I hit create crude hypos, they're actually there. And what's kind of interesting about that is by feeding in what the light ends are and a little bit more about the boiling points, you can actually get the kind of the corresponding estimated kind of physical properties from. So basically what you would do is you would just literally measure temperature and the amount that was boiled off, and that would actually be the amount of each of these hypothetical groups. Okay, and I'm just showing you that as kind of an aside. You don't need any of this unless you're dealing with hypotheticals, so we're just going to stick with these selected compounds for now. I just wanted to make sure you could see how you could add a really complex oil mix if you wanted to. Right, now that our component list is ready, we will actually close the component list and then hit the home view here. Oops, sorry, I shouldn't have closed it. We'll just go to components here. And then what we're going to do is make one other choice, and we're going to pick our fluid package. Now what a fluid package is it's the way that you're going to estimate all of the physical properties of your system. And in the oil and gas industry, what we're going to do is add Peng-Robinson most of the time. Now there's a few things I just want to point out to you here. There's a lot of different property packages here. All of them have better and worse applications for them. Peng-Robinson's kind of a good universal simulator, but it has a problem with water. And so you'll notice here there's a special tick box for special treatment of water. And what it's doing there with water is it's just going to make sure that water stays as its own separate pure phase rather than mixing in with anything. You can see also there's sour Peng-Robinson, so that's what PR means there. That's a specific version adapted for when you have sulfurous crude. And you can also filter it here if you want to, but you can see there's like, Sauve Ried Le Quang, Sauve Ried Le Quang's there as well. Van Laar's a classic one if you're familiar with it. I don't know why I clicked it. Whenever I click Van Laar, it takes forever to load. Anyway, you should generally pick what package is useful for the current thing you're trying to do. And actually inside Unisim, you can change what the fluid package is for a particular piece of equipment, right? So what you're doing right now is just choosing the general fluid package that you'll use by default. So Peng Robinson isn't a bad choice here. What's quite interesting and what's quite nice about it is you can actually start to look at the parameters. So if I hit parameters here, there's nothing given here, but if I go to binary coefficients, you can see some of the kind of key coefficients that are put in to actually calculate the properties of the system. So for example, this Peng Robinson, it only has one interaction parameter, so you can look those up if you want to have a look at them. Everything else is probably stuff that you don't want to mess around with until you get to a specific application that needs you to alter it. So right now we're pretty happy to just say Peng Robinson. Do you know what, we've lost some of our view, weirdly enough, so I might just try starting that again. So I have no idea what I did there, but obviously I've got a different setup here. But sometimes it's kind of, there are so many options on here. You can easily misconfigure something, so sometimes you just have to start again. But there you go. I've started again. Peng Robinson, special treatment for water. I'm happy that everything in here is the way that it normally works, so I will stick with that. Right, once you go back here, you can close this if you want to. If you ever need to get back there, you just hit home view. And what we're going to do is enter a simulation environment. Now, in the simulation environment, what you have is this kind of main window here where you draw out the things you're interested in. And over here, here's your toolbox to draw the stuff out. We're going to look at a material stream. So what a material stream is it's a flow of matter, right? So if I want to click in here, I'm going to define what is flowing through my system. Is this a flow of methane, ethane, propane, and butane, or what? Now, the way that Unisim works is it's telling you right now it doesn't know, it hasn't got enough information. That's why this thing is yellow. When it's green, it's got enough information to work out everything about the stream, and it can be red when there's an issue. For example, you put something conflicting in. So right now we haven't got enough information, nothing's filled in here, and what we've got to do is specify something about the stream. Now normally we'll know something like the temperature, so we'll say 5 degrees C. I can choose the units here. I'll say it's 5 degrees C, and we'll say it's 10 atmospheres. So I'll just pop in here, choose a convenient, no, 10 atmospheres. Right, there we are. So it's now at 10 atmospheres, 5 degrees Celsius, but still not everything else is filled out. And what I need to do is put in molar flow and a few other things. But what I like to do is I prefer to specify the flow rates of the things coming in. So I'm going to just hop down to composition. It's freezing on properties because it's trying to work out stuff that it can't work out yet. So I'm going to click on composition. Up here it says mole fractions. Rather than put mole fractions in, I find it easier to put in mass flows. So I just, if I'm going to dial things in, I'll say, okay, I want 1 kilogram per second of methane. I'm going to have, whatever, 20 kilograms per hour of ethane, 100 kilograms of this, whatever I think my flow is going to be, I throw it in. Okay, so that now gives me a flow, and in kilograms per hour, I know the total flow rate down here. And if I hit mole fractions, oh, I didn't want it to do that. Oh, that's annoying. It didn't normalize it. Okay, let's do that again. So we'll do 100 here, 90, 50. And I'm not going to put water in at this point because I want to talk about that later. Okay, so we've got some flow rate in here, whatever it is that I'm interested in. I'm going to hit OK. Now what you'll notice is something interesting's happened. It's straight away worked out how much of that total mass flow is there as a vapor and how much is there as a liquid. So we actually have a liquid phase in the system. And that's really cool, right? Straight away, that's a flash calculation for you. It's already happened. And if you wanted to use K values, right? If you wanted to actually do some kind of K value calculation, then these are the K values available for this system. I'm not sure what the mixed light and heavy versions are, but they seem to be absolutely equivalent here in this case. So you can use whatever one. So if you need to, like now of course, right, all I had to do was I had to specify temperature, pressure, then the flow rates of everything, If I specify mass fractions or mole fractions, I would need to also specify the mass or the molar flow, one or the other. But once I specify those, everything else is worked out. So I can also look up other things. For example, what is the heat capacity? What is the density? You know, there's a ton of properties already looked up here. So if you ever need to look up physical properties for a calculation, you can use something like Aspen. Bearing in mind, these are all predicted properties. There is no guarantee that they are correct. So there's no substitute for actually looking up a proper tabulated set of data for something. Okay, so that's one of the ways we can get some of this information out. Like we can look at what the vapor phase and the liquid phase are, but you know, we perhaps want to do something else, like figure out some kind of energy or do something else, perhaps a compression, whatever, you know. So the first thing we'll do is do a phase envelope. So if you go Tools, you can go Tools and Utilities, that's right. And I think it's the envelope utility that I want to use. And then I hit Add Utility. What this envelope utility does is it tries to figure out the two-phase envelope for the system. So I just have to pick what stream I'm talking about. So there's only one stream, right? That's stream 1. So I have to select that one. Then what you'll notice is it gives you some more properties. It gives you the two-phase critical temperature, two-phase critical pressure. But really the interesting thing is, if we hit Performance, I actually get a full envelope. So if I just make this full screen, that is the phase envelope for the system, and we've done quite a lot of work on that. We can generate even more interesting things, right? So for example, if I come here, no, wait, what am I doing? Let's move the toolbar. Yes, there it is. So if I change this from pressure temperature, which is where you see the phase envelope, to pressure enthalpy, this is actually the mollier chart, right? It's the mollier chart without the lines on there. However, you can add some of the lines. So for example, I could come up here and add a 20-degree C line, and there's the 20-degree C line for the system. So this is a mollier chart for my multi-phase, multi-component mixture, right? So very cool that you can just generate these things as and when you need to generate them. And if I take view operating point, that's actually where that stream is. So you can see here I can quickly kind of explore the phase envelope and start to think about things like, okay, how far away am I from boiling? So if I switch to PT, you know, you can see that I'm very close to actually completely boiling the system within 4 or 5 degrees of it. Yeah, we can also see things like the Crichondon bars up here. So the Crichondon bar is something like 9,000, what is that, 9,000 kilopascals, so 10 to the 5, 100, so this is what, 90 bar, is that right? 90 atmospheres roughly is a Crichondon bar. So what we'll do is, just to kind of see something a bit weird about that, is if we hop out of this tool, so I'll just delete the tool, I don't need it again, you can always add it back again if you want. We're just going to go to the stream and actually try and play around with it a bit. So if I, oh God, where's it gone? There it is. There's the stream hiding at the back. If I come up to this and instead change the pressure up to, what was it, 9,000 kilopascals? Right. And if I go to 10,000, oh, sorry. If I go to 10,000, right, it's now saying there's a liquid phase, but we're actually above the Crichondon bar. So there's no liquid or gas anymore, right? We're just in some kind of dense phase. And so if you kind of change the pressure, the temperature, say, if we change that to 100, it says it's a vapor, but, you know, if you try and iterate down to figure out when this thing boiled, you're not going to be able to figure it out. So this is junk, right? When it'll say vapor or liquid, whenever it's above the Crichondon bar, and it doesn't really matter what it says, right? There is nothing up there, right? You're in the dense phase liquid. So that's just something interesting to know about it. Okay, what else could you do? Well, let's make a compressor, right? So if we add well, we're not going to make a compressor. The first thing we're going to do, I'm just going to delete that. Yeah, the first thing we're going to do is put a separator in. You know what we'll do? We'll actually put a 3-phase separator in here, and then what we're going to do is connect these streams I can never remember how to do this. Ah, yes, that's it. So we use the connector up here. So we switch into attach mode. We hop over this thing and we connect its output by dragging to the input over here. And then what we need to do is create streams for the outputs here. So we're going to connect a water stream, an oil stream, and a gas stream. And we'll just connect those up now. So I'll click this guy and put it in attach mode. Go to the heavy liquid and attach that to here. And then I'm going to go to the oil. That's the liquid product. Wait, what happened there? Very strange. It seemed to create an extra stream. So I'm just going to delete that stream there once I go out of attach mode. I do indeed, and then I'm going to drag 5 here. Okay, cool. Now what you'll notice is I just added this separator, and now if you have a look up here, there's 100. So if I hover here, there's 14.41 moles flowing in, and they're all coming out as a gas, and that's because this stream I put up above the Cricondon bar. So yeah, it's all gas. So what we'll do is just drop this down to a more moderate pressure and temperature. We'll actually drop it and make it, 0 degrees C, just so we have some liquid coming out. And now what you'll notice is this 3-phase separator. We have 14.41 kilogram moles coming in. Now we have 13 moles of gas coming out the top, and we have 1 kilomole of 1.385 kilomole coming out through this liquid stream here. But now at the bottom you see nothing coming out here, and this is because water would normally come out this place, and we haven't got any water in here. Now if we come up to this stream and we just suddenly add some water in there, so I'm just going to put 100 kilograms an hour of water in, and it brings up that thing all the time, but you can just hit OK. So I've added an extra 100 kilograms of water in there. What you can do is have a quick look at this stream, and this stream is now 5 kilogram moles. Interesting. And its composition is primarily water with a little bit of CO2. Okay, that's what's happening there. So I was a bit wondering about the value, but you could see some of the CO2 is dissolved in the water. One of the things you will note though is there is absolutely nothing in, there's no composition overall in of any of the oils. So the Peng-Robinson equation of state, this is a great example of it, just ignoring all oil and assuming all the oil comes out in the oil phase and not in the water phase. You'll notice that these vapor phases, right, have a composition, right, which is oil and gas, and so does the liquid, and that's a bit confusing, right, when it's 0 here, but then these phases have it, and it's because those phases don't exist. So if I change the basis to mass flows, what you'll notice is it's all 0, right? So there is none of that phase, right? So the mole fractions could be anything because there's nothing there, right? There's no actual flow of it. So as soon as you put it in mass flows, which is my preferred basis, you can actually see, okay, there's only this aqueous phase here, that's the special phase, the water phase, and everything's inside that. Okay, what else can we do? Right, well now we've got this gas, right? They're coming, and this is a pure gas phase here, we can see. Again, you can see there's a phase fraction here, and because there's a 1 in the vapor, that means everything's in the vapor. If I look at composition and switch to basis and switch to mass flows, you can see everything's in the vapor phase. What I can do is then try compressing this. So I'm going to use not an expander, there's my compressor. I'm going to use a compressor. I'm then going to attach this stream to the inlet of the compressor where it's larger, and then I'm just going to use the attach mode and see if that lets me just kind of no, I'll put a mass stream there. I'll use the attach mode. I always have to relearn this. Okay, come on. No, that's not, I don't want the applied energy. Is that the output? Yeah, that's the product stream. There we are, to the product stream. It's still not happy, right? And the reason why this isn't happy is because it can't figure out what it's meant to do, right? So it can't tell you what's coming out of it. A separator's job is easy. It's just split what comes in. But a compressor, it has to know something else, like what am I going to do? And what we're going to do is we're going to put an energy stream into it. So I'm going to put an input energy stream, and I'm going to attach that in. And attachment mode just doesn't keep working, and I'm going to attach that to into the shaft. So of course compressors, the power goes into the shaft of them, so that's where that attachment point is. And now the compressor is a little bit happier, but this stream is still light blue. It still can't figure out what's happening. So this energy stream that I've attached is what's the energy going into the compressor, and it's still it's unknown as well, right? Everything gets a little darker once it's known. This is darker, it's known, it's happy. This is light, and this is light, because none of these are really determined. So what do I need to do? Well, I need to say what the compressor is going to do. So you'll notice here it's got an inlet, and these are the streams coming in and out of it. But what the thing I really want to do is talk about the parameters. So there's two things I can do here. Or there's many things I can do. First of all, I can choose its adiabatic efficiency, or I can enter its polytropic efficiency. But the thing I'm going to do is just say what should be the pressure increase. What's the delta P? So I'm going to say that this increases everything by 10 bar, right? And as soon as I do that, as soon as I give it enough of a specification, it figures out absolutely everything else. So it figures out the polytropic efficiency, what the pressure ratio is. Obviously the pressure ratio, the inlet was 1,000 kilopascals. I'm increasing it by 1,000 kilopascals. That gives you a pressure ratio of 2. And it tells me now the work. So it's going to take 7.3 kilowatts to do that. What's really nice now as well, if I go to this outlet stream, I can see the temperature, and the temperature's increased, and that's what you expect, right? From a compressor. A compressor will actually increase things, increase the temperature of things. The other thing I can do is I can try deleting this and do something else, right? So I can try deleting that and trying to set something else. I can also choose different types of curves as well. You can also, if you want to, there are, like, if you really get into this, there are adjusters. So you can actually say, for example, I can put the pressure increase here. Well, let me see if I can do this. It's been a long time since I did this. So I'm going to say put 1,000 in here, but maybe I just want this compressor to compress until the stream reaches some maximum temperature. Well, you can use an adjuster to do that, right? So an adjuster sits somewhere, right? And then what you do is you want it to adjust something. So I'm going to select stream 3, right? So stream 3, and I want it to adjust. It's no, sorry, I don't want it to adjust stream 3. I want it to adjust K100, so the compressor. I want it to adjust the thing that I just said, which was the pressure increase, right? You see the pressure increase in here. I think it's this pressure ratio. Where is it? Well, it depends which thing we want to do, but I'll get it to change its duty, right? That's the same thing. To change its duty, right? So change the duty of this compressor. And what am I going to do? Well, I'm going to get it to change it so that stream 3, its temperature gets to 120 degrees C. Oh. And the issue I have here is it's moaning that this was specified before the adiabatic efficiency is, but it has a new calculation. And it's saying that general simulation is over-specified. The problem is I've given it too much information. So what I think the issue here is that I told it the pressure increase, and then I told it to also change the duty, and it can't keep that pressure increase, change the duty, and then not change the efficiency. So I'm just going to delete that pressure increase, and then I'm going to tell the simulation to try and run again. So you see it went to stop. So it said it had an issue. Basically too many things were set, and it went to the solver holding. Now I'm going to say solver active, and it's running. And now all of a sudden I've got this adjust. So now this temperature of the stream is 120 degrees Celsius, and it's varying the duty of this. So I can actually tell it, basically, I can figure out how high can I pressurize the stream before it hits 120 degrees C. Yeah, I think that's everything I'm going to do in this Unisim aspect. You've seen how I've there's a couple of other things. For example, we could now then cool the stream, and that's quite easy to do. We just essentially attach that outlet stream to the inlet of a heat exchanger, put another outlet stream on there, attach that to this guy. We then need to put in a heat stream and attach that to the inlet of this, and then somehow set this. So we probably want it to, get our outlet temperature. We can also set the outlet temperature another way, right? So I showed you how to do an adjust, but another way of doing it is you can just click the stream and actually just say, look, I want it to cool it down till it's 25 degrees C, and you notice the stream is saying unknown pressure. I've got two choices. I can say what the pressure is here, or I can click on this guy and actually go to parameters and say, you lose half a bar, or pretend it's an ideal exchanger and say use 0.5. But I had to give something on that, and that then allows it to solve. And everything else is there, right? That tells me how much heat I need to remove. I now have this thing cool down again. What you'll notice is some liquids come out, and that's because I've compressed the system, it's heated up, and then I've cooled it down. That'll cause liquid to drop out. I would then, if I was building a compressor train, put another separator here and carry on, right? But that's everything I kind of want to cover out. That's all the functionality inside Unisim that I really wanted to show you. If you have any more questions, please let me know, and I'll show you how to do more things like glycol absorbers and so on.